Hey, everybody. It's me again. I'm back. Hey. So Nate made his way from the table over there all the way up to the stage here. He has a microphone in his hand. He has slides on the projector. So if you want to give him your attention, we're about to get an awesome talk about JAMstack. So Nate, please take it away. Thank you.
Hello, everybody. I thought we were taking like a break, and then we didn't, and now I'm embarrassed. I'm on stage now. So I work for a company called FaunaDB. I like to say we're based on planet Earth because we're all remote. So I work in Philly and no one else does, and it's kind of awesome. So I'm happy to talk about remote work stuff too afterward. But I love working for FaunaDB because we build a database, and building a database is hard. And that's fun to solve hard problems with smart people. But today I want to talk to you about the JAMstack. Does anybody here use the JAMstack or know you use the JAMstack? How many of you have like heard of this but don't really know what it is? Awesome, great. Now I know where we're all at. This is exactly what I wanted. Great. So before I worked at FaunaDB, I used to work at MongoDB, and before that at Red Hat. And at both of those places, I was a consultant. So for years, I would go around to different clients and like help them build stuff or build stuff for them or fix their broken stuff or whatever else they wanted me to do. If they wanted me to sweep the floors, I probably would. That's what consulting's all about. And I really liked getting to see a multitude of places really solve different problems and run into a lot of the same issues. So that was kind of a nice way for me to see kind of where the corporate world was in that space of time. So what I'm going to do is talk to you about three different things. The first one is that you can simplify your app behavior by using the JAMstack, and some of you actually might already be using it. Tell you to use GraphQL everywhere. Anybody else use GraphQL? All right, cool. We got some people really love it, like really love it. And then I want you to see that you can free your apps from the limitations of scale by using FaunaDB. So first, let's talk about the JAMstack itself. And we're going to do that by looking through the eyes of a request. Now, this is a request. And nothing brings this request more joy than to bring you web pages, like really fast. So let's take a look at static web pages because those are super nice and easy. You take a browser and you fire this little request at it, and it's like, yeah, I want to go get something, and hits a resource. In this case, it's an AWS bucket, could be anything. And bam, it comes back with the web page, and everybody is super excited. Your users have your page, and your request dies a happy death. But we've also got dynamic pages because not everything can really be served statically. And the way that would work is your request hits some maybe node server in this case and wait around for a little bit till your page gets kind of like made for you and then goes back. And like, that's okay, but it's not nearly as exciting or rewarding as that path we saw from the static site. So what's happening behind the scenes here? I want to get rid of this window. Ta-da. So in a node situation here, we might have a MongoDB database and some API we want to call. And so we make that call and we make subsequent calls to these other APIs. So we're making a query and some other API call, and we get back all this information. Now on our node server, we're going to be able to build something back for them that has all this data for them and send it back. We finally have that and it displays to the user. So this unfortunately makes a request super sad because a lot of its life is spent waiting, and that's not what it wanted to do when it was born. So the problem is that this is not new. This is really how we've been building these dynamic web pages forever. So even if we think we've got some new technology, we've really been doing this pattern for a long time. So maybe we're back in 1995 using Netscape to grab something off of disk. Thankfully, we're not. We could be using a Microsoft stack, getting stuff out of SQL Server with .NET code. Doing some Java and Oracle work, did some of that. We could even have something more modern. We're still following the same pattern. But you might look at this and say, wait a second, this is serverless. This solves all our problems. Even if I don't know how it works, it solves everything. And you might be right. So let's take a look and see if we can take advantage of this serverless architecture to build something slightly different that we couldn't in previous years. So yes, this is serverless. Thank you, slides. So here's a different way we could build something. And here I've chosen to use AWS Lambda, but we could use any form of serverless function and patterns. So here we have two separate places. First, we fire a request off to the first Lambda that's going to get something from our static bucket. You don't even need that Lambda there. You can hit the bucket directly, but I like symmetry. And we get back the static information that gets displayed directly to the user. And with that, like most web pages, comes with some JavaScript. Now, that JavaScript we can actually use to go call this other endpoint that goes and gets that dynamic data that makes our website so interesting and personal to the user, in this case from DynamoDB. Now that request can fill in that information when we need it, where we want it. And none of these requests had to sit there waiting for anything to get generated. This is the JAMstack. It's a different way to build our apps where we care about the way our network calls are done. We've shifted it from that middle tier with that node server and pushed it out to the client on the browser. So how many of you have built something like this with or without that Lambda where you just have like something hitting a bucket, an AWS bucket? How many of you found this to be truly joyful? Wow, I'm jealous. I built my first I want a job, here's my creds webpage like this. And I am so embarrassed to say it took me a month. I didn't have a Lambda in there. It was oh yes, okay, you're with me there. There's so many little settings to hit. And if you wanted HTTPS instead, and I'm like, oh no, they're not gonna hire me if I don't have HTTPS on my site. I'm panicking in the background, trying to figure it all out with undocumented features. This sucked. I'm sorry, AWS, but I'm not your friend. How many of you have used Netlify? Okay, a lot more people have. How many of you found this to be a pure set of joy for you? Okay, a lot more hands. This is what I think we wanted serverless to be before we knew what we wanted. So if you haven't tried Netlify yet, I just like them personally. You should totally check them out. So this is what the JAMstack is, and it lets the request do its job faster. But there's more benefits to the JAMstack too. So it also provides some on-demand scaling capabilities. So let's say you built this app here with the node construction in the middle with MongoDB and some API that you call to make some really cool app. And then all of a sudden, you hit the front page of Reddit. Everyone loves the thing you built. I mean, you love it, who wouldn't? Unfortunately, you only have one server deployed because you just built this for yourself and your friends. And it can't handle all of the requests that get made to it, which means you missed a really big opportunity, and all these people who liked your cool idea don't get to see it. So on-demand scaling with something like Netlify or AWS, they all have serverless functions. They can actually scale up to meet the demand that comes in. So if you're using these serverless functions, we don't have to worry about how many we had deployed and have to think about when we're ready for a spike of users. We get that scaling built into the app. This is the request living its best life. It gets to bring you back stuff super fast, and it's not even competing with any of the other requests. It's great. So the JAMstack, all together, you'll see it with the letters JAM to stand for JavaScript APIs and markup, but really we're sending pre-built markup pages and we're using client-side JavaScript to call APIs. That's what makes an app a JAMstack app. Now, how many of you have built a JAMstack app before? More of you, yeah, awesome. So that's how you can simplify your app behavior by using the JAMstack and thinking of that as an architectural design choice. So the next section is about GraphQL, and you should use it everywhere. Anybody else agree? Okay, yeah, a lot of the people here love this. So what is GraphQL? It's a common interface for a lot of different data sources. So maybe your app has a maps API it needs to call. It also has some other separate weather REST API. And then it has a database it needs to hit with a query language. Cool. It's going to take all of those with the same common way to query them in your front-end app. And it's going to do all the hard work of reaching out to the internet and splicing it all together and getting you the objects that you asked for. So you have to do less of that. And you can use GraphQL with pretty much any database. Even if that database doesn't explicitly support it, you can find a driver that was kind of like built to do that, which is pretty neat. So if you have a favorite one, you can probably use GraphQL with it. And so I'm going to run through a real quick example of what kind of GraphQL looks like in code, because I need to see examples myself. And this is the most simple app. I cut it down from a bigger app. Who owns this car? Really important question. If you run a parking garage, maybe it really is. And so we're going to actually write down some types here. And so we have users of this system, this parking garage system, where we have a username and they may or may not have a car. And here we have a list of cars that can't be null. We're also going to define what a car is. A car is the combination of a plate number that is a string that can't be null and a user from that other type definition we have from before. So we know who owns this car. And we're going to write down the queries that we expect to build here. So we say we want to query a user by the plate number because we're going around scanning the plates, making sure they've paid for their subscription to our parking garage service. And if you take all of that, it adds up to your schema. And so as far as FaunaDB goes, we love GraphQL and we've kind of built it into our product on the server side. So if you upload that schema file, all those little definitions you gave us, we'll build out the collections and the indexes and you're ready to go. You don't have to do any of that because you've already defined it once. There's no reason to go define it in another part in your stack too. So I find that super convenient. So we want to like put data inside the database. We'll use something called a mutation, which is a GraphQL keyword. And here we're putting in the username, Bob. And if we want to fire that query off that we've said before, we're going to call explicitly what we want back. So you can see at the bottom there, it says plate and owner. Those are the two fields that we want back. I didn't want to put an example of merging everything together, even though that's the coolest part about GraphQL. You can query for different sources and ask for one object back. And that is like the coolest thing ever. You ask for what you want and then it magic goes and gets it. So that's the main killer for GraphQL. And so really with GraphQL at the center of your application, you can make queries all the same way and kind of get rid of all the hard work of trying to memorize how to hit all the different services. You write it down within GraphQL once and then call it exactly how you want it to be, whether it's a database or a REST API. So that's why I think you should be using GraphQL everywhere. And next we're going to talk about freeing your apps from the limitations of scale with FaunaDB. So there's two components to this section that's more databasey. I want to show you that the database can often be a bottleneck in your system and that distributed async transactions really are a solution to this. So let's go back to our JAMstack app that we have. And this time we're going to use a Postgres database. This is really any of the legacy databases, not specific to Postgres. And let's say we have a large number of requests that come in. Awesome, we're prepared. We use the JAMstack. AWS Lambda scales all the way up for us and lets in those requests like we expect. But Postgres can't use the same strategy because it might have like a terabyte of data. It can't just copy itself instantaneously on the fly and serve more requests. It's a box that has a fixed size. And you chose that size and it is probably not big enough. So you run into the same problem as before where your requests don't get served and everybody's sad. So when we're using a database, really all we want, myself included, even though I love them dearly, I just want to shove data in it and run away. And I want to be holding that okay symbol. I just want to say, yes, you said everything's okay. I believe you. And I think if that's how you think about databases, you're thinking about them the right way. So I want to show you the way that we get high availability through a system like Postgres. And this strategy is called active passive. So when we hand data to this instance, let's say it's like an insert, could be an update or a delete, but we're handing some change to this database. And this active instance is going to take that write and then pass it along to the passive instance. Then the passive is going to say, hey, I got that. It's totally on disk. I'm ready for failure. And the active is going to be like, okay, great. We both got this. So at this point, I know that both servers absolutely have the data that I wanted to be there. Now, this okay is meaningful. This is great, because once I have that, I know something about the system. I know something about where it lives. I can run away and know everything's going to be fine. Now, the way it doesn't work in Postgres, but it does in some other databases, is when you send data to the active node, you get an okay back right away. That is not how it works in Postgres. But this leaves us open for something like this. So if at this point, before it sends the data over to the passive node, it dies. This is our worst nightmare, because now the whole purpose of that passive node is to serve data when that active node goes down. And now it doesn't have that data that it should have. You're holding it okay, thinking everything's fine, and no one is reading your change. This is the stuff of nightmares for me. And this okay really is a lie. So it's hard to trust systems that behave in this kind of way. Now, one of the reasons that systems will behave this way is if we did it the right way and we wanted to scale up to more than 2 nodes, all of a sudden, once one dies and it can't take anything, the entire system is down. That's not really high availability anymore either. So we're kind of stuck in this limbo with the old way of doing things. So why are we using these old systems? They're still super popular. And so I'm going to talk about transactions and what they mean and why we care about them. And we're going to talk about ACID transactions. I'm going to go through all these letters and what they mean, because ACID transactions are the golden standard for transactions as a whole. And it's why we still use these older systems today. So A is for atomic, which really means all or nothing. If you want to put 2 documents in, you're going to either get both of them in or none of them in. And C is for consistent. The whole state of the database is going to be valid before you start this transaction and after. None of the things like unique indexes are just going to suddenly break because you ran a transaction. I is for isolated. So whether you run it one at a time or in parallel, the result is going to be the same. So when you run your tests one at a time and then you throw it at the world and have everybody do everything parallel, it behaves the same way. That's amazing. D is for durable. Once it's complete, it survives outages. Power goes out, you axe the cord, it's fine. Everything's still there. Now, the hard part is that these systems really only do it within one node. We saw that the active node was a single node. If we want to distribute that, where we partition our data, where some of it lives on one server and some of it lives on the other, and we want to make these guarantees, these ACID guarantees about that distributed data, now that goes from a hard problem to a really hard problem. And so for a while, we kind of only had 2-phase commit as an option. Google Percolator uses this, which indexes the entire internet. So it's cool, it works, it's good. But it's a blocking process, and one component of it, called the coordinator, can't be distributed. So at some point, everything has to go through one place. That doesn't really match with like the kind of apps that a lot of us are building, where they're supposed to be globally distributed for like everybody. We can't necessarily have all our data go through one point. So in come a bunch of these other companies that built some really cool products to get around this issue, where they let you globally scale your data. And they do that, unfortunately, by relaxing these ACID transactions. You no longer get these guarantees, because instead of having those, you get to have the scale. You can write all over the world, you can read all over the world, but you're not sure necessarily what you're reading in some cases. Depends. So you have to know a lot about the inner workings and the architecture of each database in order to really behave with it in the way that you want. And so if you know what you're doing, this is great, but you can't have that mentality of, I want to shove data in, get the okay, and run away. That no longer works here. So if we go forward in time, another option popped on the market called Google Spanner, and it gives you ACID transactions at scale distributed, which is super cool. And it does this by requiring each server to have super precisely tuned atomic clocks, which is really hard to maintain, but Google is really good at a lot of things. The problem is that the penalty for clock skew is inconsistency. You're trusting that whoever's managing this algorithm, the database underneath it, that these clocks will never go askew. And then in comes Fauna. Surprise, we also built a distributed ACID compliant database. But it's based off a completely different algorithm called Calvin, comes out of academia, and it doesn't use any of these clocks. So I want to show you what our architecture looks like and how we achieve what we do. So I'm going to walk you through a simple write, but first I want to show you our architecture. So these 3 circles are 3 different geographic locations, and we'll call those a replica. So in each replica, we have a complete copy of our data. So if we have something on like the West Coast and then Central and the East Coast, they're each going to have a complete copy of our data. And you can read or write from any one of these nodes. It doesn't matter which one. There's no primaries or actives or passives. And each circle has a partition in it. So here we have 3 different partitions. Each full set of data lives on lives across 3 separate servers. So in our application, when we fire off a request, in this case, we'll try and make a change to the database, like an insert. It goes into something called the transaction log. This is the first part anything goes into. And it's made durable there by making sure it's on a majority of the servers that are participating in the transaction log. Cool, we did it. And then it's going to apply to one of the nodes. In this case, it's a single document. We're not doing anything fancy. And so it lives there. So once it's applied there, we know it's good to go. It hasn't violated any of the constraints that we have. And we can get an OK at this point. Now, as we run away, that data is going to distribute across the rest of the database. Awesome. So let's see what happens when we do it with more than one document. We're doing one of these ACID transactions. So we're going to have the same thing where we say maybe we have 100 documents we want to throw in the database. In this case, we write them all to the transaction log. It's made durable. And then we apply a bunch of checks here to make sure everything's going to go smoothly. And then we actually apply it to one of the nodes again. Now, this isn't all 100 documents. This is probably like 33 of them or something. And then we get the OK back here, because everything still lives on disk in that transaction log. It hasn't just made it to the data nodes yet, though. So we can still run away knowing everything is guaranteed to make it to the other nodes eventually. And it does. Now, for those of you who've been listening very carefully, I said you could read and write from any node, but you might look at this and say like, oh, but some of the data hasn't gotten there. Like, how do you read it? It's not there. I will show you. So in that case, what we have is a immutable storage engine. Whenever you make a change in the database, it doesn't actually overwrite the thing that was there previously. So let's say we have an initial state where you have 2 documents, A and B. They're in state 0 at this point. And then we go and make a change to A. It's now stored as a diff. We didn't overwrite the old one. We just said, hey, we changed this one field, and we put that in the database. Then we have a change to B, and maybe we fire a transaction next that changes A and B at the same time. So now we're storing the history of our documents like this. When we run a query, it always has a timestamp on it. So when we query at Q0, we're going to get this pair of documents. If we query at Q1, we can get this pair of documents where it's A1 that changed, and we rolled up B0 from where it was before. Same here with the third. And the final one, we get that change that was made at the same time. So if you're waiting for data to come to the node, you fired a query, you fired it with a timestamp. And that node knows how far up that it is on the transaction log. It knows how many transactions it is behind. It's just going to wait for that timestamp to pass. So if no changes come in after that timestamp, it knows it already has the data you wanted. If changes do come in, it's going to give you the latest. So rather than trading this scale for consistency, you instead just have to wait a little longer. And to me, that's the ideal trade-off. So this is a map that I pulled off of our website of all of the locations of our nodes that we have right now on our cloud instance. So if you start using it, all of your data is replicated all over the world, ready to go for all of your users. You can feel free to try us for free at fauna.com. You can follow me at Twitter and Fauna on Twitter as well. So I'll stay around for a few questions, but that's all I have.
You know the drill. I'm going to run it to you. Anybody have any questions? Never mind, I lied.
I'm going to do the running.
I like it.
So when you're storing the entire transaction history and you're querying it, doesn't storing the entire history of transactions take up a lot of space and storage?
Yes.
Absurd amounts.
So we don't do that. We don't store everything ever because we have to get rid of it at some point. Right. So the default on the storage engine itself is 30 days. And it turns out the diffs are small enough that that actually doesn't take up too much. And as far as the other place that history is stored is that transaction log. Once we've applied all of the changes everywhere, it falls off the end. So we only keep things as long as we know we need them.
Awesome, thanks.
That's also a route,
Following up to his question, how do you guys prevent something like a DDoS attack from taking down the DB in the case that you have some massive amount of data coming in at the same time, blowing out whatever your preset like swap size was?
Great question. So how do we handle someone doing too much work? So what's nice is that most databases who have cloud offerings make you pay for your whole thing. So if you screw it up, you just screw it up for yourself. We like to have that same mentality. If you screw it up, you just screwed up for yourself. But we want to lower the cost for everybody by having an efficient shared environment. And so people are running their companies off of our shared environment on our cloud product, because we've built in a bunch of features to make sure that when you do something, it doesn't affect the entirety of the cluster. That was one of the goals when we first made this, is that it does seem kind of wasteful and inefficient for you to set up a giant database cluster and hope you don't ever use more than half of it. And that raises your costs a lot. That being said, we do have an offering for doing a managed cluster if you want to do that old model of and pay extra for that dedicated hardware. But that is part of the system we've built. It's called a quality of service. So we make sure that we read everything that you're doing and we kind of keep you in line. So you shouldn't have to worry about anyone else ruining your ability to use your database. Great question. So we got a few more.
Hi, this is actually the second time I've heard this talk, but I just had 2 questions this time. And both of the answers might just be read the Calvin paper, so I apologize. The first is, how did you guys get past syncing the timestamps without atomic clocks so that your queries and transactions are accurately timed? And then the second, and again, this may just be read the paper, is how do you assure acidity given the fact that, let's say, the rightmost node on your diagram, I'm explaining this very badly. How do you ensure that, for example, a record that's trying to be updated hasn't already been deleted on some other node? And if the answer to that is read the Calvin paper, it's like the 5th time I've come across it, so it's fine.
Cool. I mean, yes, you could read the Calvin paper, but it's dense. So I'll try and give you like a better explanation than just that. So let's start with the first one, which was how do you avoid having to coordinate all the timestamps? So we do have to care about timestamps a little bit, but they do not have to be accurate. So if they're off by like a couple seconds, it's really not that big a deal. We do that. So we're actually using logical timestamps to keep with time. Though when I say everything comes with a timestamp, it actually isn't like a reality time. It's like a cluster time that we all kind of agreed upon. Part of that process of putting it into the transaction log actually is everyone agreeing with Raft. This is the time I believe it is, and this is the time I'm assigning to this particular set of transactions. You all belong into what we call an epoch, and this is the time interval that matters for you. And because we all agreed, that matters. If the clocks are really, really, really off, then we're going to have an issue on on their ability to agree on these things. And really what we're going to do is we're going to see a lack of availability of the database, which that's terrible. But if your database clocks are off by hours, that's also terrible. And we don't ever see a loss of consistency, which is the worst nightmare for anyone who runs a database. So if you do pay that price of not paying attention to your ops like you should, then you're just going to have the database not be available for a little bit, rather than lose all consistency and run around panicked. And then the second question was on how do we keep ACID compliance when we were not sure what the state of the data is on the other side of the cluster. So we could run So the way that this works is that we have, everything has a complete ordering, and that's actually unique to the way that Calvin works, is we assign that ordering when we first insert things into that transaction log. So whether it's happening on that left side of the cluster or the right side of the cluster, it's still happening in the same order. So if it's gonna work at all, whether you did that delete on the one side and then did the update on the other, we already agreed when everything entered the cluster first, what order it's going to happen in. So if it works on one side, it has to work on the other deterministically. We'll never get a different result when we write to different nodes. I'm happy to chat afterward if that's not satisfying, because I know it's like weird stuff.
Distributed across the cluster. Is that what you're saying?
So the question was, is the log distributed across the cluster first? And so that, I will use the word replicated. So we will agree on everything in the transaction log first and then distribute it. And so that agreement across all those nodes that are participating are what's deciding that order. Now, in real life, we actually do distribute that too. There's 3 of those transaction logs, and it's a lot more going on underneath the hood, but that is exactly how that works, is we set everything first, and then we read from that from the rest of the nodes. Awesome.
This should be a relatively easy one, but so is that why it has to be over 51%? Because otherwise you wouldn't know that every transaction was at least known to like every other, like that there has to be overlap of every transaction between 2, like in the transaction log. That makes sense?
You're asking about the transaction log itself when we write?
Yeah.
Yeah, so because it's all about Raft. So if you know how Raft works from like the MongoDB voting protocols and stuff, it's all the same in that regard. So we need to have a majority of the nodes up. One of the reasons is for partition tolerance of the actual Raft participating nodes. If you don't have any nodes go down, but you cut the cluster in half, you need to make sure you know which half has like the real stuff. And so in a 3-node cluster, the side with 2 has a majority, and the side with only 1 knows it doesn't have a majority and knows that it can't actually take writes. So when you need to have more than half, you can actually still complete those Raft consensus agreements when you can't otherwise. So if 2 of those nodes are down, you actually can't make writes.
We have time for one more question.
As the end user, can I query against the immutable store to get like a point in time slice of my data?
Yes. How many of you have deleted something and were like, it doesn't hurt as bad anymore. It's still there. So yeah, I love that as a developer. You can query it for like right now, or like, wait, I want to undo what I just did. You can totally read it back and write it again. So yeah, that's one of the benefits of having that.
Awesome. Well, thank you so much, Nate. Really appreciated the talk. It was just as good the second time, if not better. So let's give it up for Nate.